Okay. So for continuous case, for the continuous cases, some examples of self-adjoint operators, which is almost the same thing as Hermitian operators. Examples of them are, say, position. So this is, say, the position operator. But for operators, it is when there is cause for confusion, it is usual to denote them by a caret or a hat. Okay. So the position operator is actually nothing but the position. It's a number. So the operator in this case is just a number. The momentum operator, which is denoted by P. So these are vector operators, right? Because they have three components. And that's what I mean by this arrow. Not all operators have to be vector, as we shall see. So the momentum operator is given by minus I h bar, the gradient operator. So if you are working in a one-dimensional system, then this becomes just the number x, and this P becomes minus I h bar d by dx. Okay. And then, for example, here's an example of a Hermitian operator which is not a vector operator, the energy operator, also known as the Hamiltonian. And this is perhaps the most important operator. Well, all operators are important, but this is the central object that describes a system. And it's usually given by P squared by 2m plus the potential energy. So what is V of x? So for example, for a harmonic oscillator, we know that for the classical harmonic oscillator, for the classical case, the potential is 1/2 kx squared. So for the quantum case, it's given by V x hat. And what we do is that we just replace x by x hat squared. But we have seen that x hat is nothing but x. So it's just this thing. Okay, so anyway, these are subtleties that is not going to concern us. So this is an example of a scalar operator, at least in non-relativistic physics. In relativistic physics, H is actually part of a 4-vector operator. Okay? But we are doing non-relativistic quantum mechanics here. And then there is angular momentum. So this is also known as orbital angular momentum, to distinguish it from spin, which also is a kind of angular momentum. But that's also, it's actually not a vector operator. It is defined by the x operator cross the p operator. So this is not a vector operator. Can anyone tell me what kind of operator it could be? Okay, give me 1 minute, think about it. I'll be back. I need to refill my coffee, and then I will hear your answer, okay? Just 1 minute.
Will that be the energy operator? We already know what the energy operator is.
স্যার কি জিজ্ঞেস করছে?
The L x cross p, what is that operator L? That's the question.
So the question, so x, so this is a vector operator, okay, and this is also a vector operator.
Naively, I might say a tensor, but I don't know if it's
What is your naive answer, Nahid?
tensor. I just thought it naively, not sure.
Yeah, a tensor is a general name for vector. Okay, let me just tell you. So suppose that you have a, you have a vector in space. Suppose this is the vector. Say this is x. So this is x, this is y, this is z. Now, if you apply the parity transformation to x, what happens to x? It doesn't have to be an operator. We can just think of it as a vector.
It flips.
So when you, sorry?
It flips, right?
Yeah. Parity flips it, right? So what happens to, so this is how a vector, this is how a vector behaves under parity, okay? This is an important concept. Under parity, a vector picks up a minus sign. Now, momentum is mass times the velocity, and velocity has in its time and x. So under parity, momentum also, sorry, I keep on using hat here, but here I just want to use vector. Momentum also picks up a minus sign, right? So this is also how a vector transforms under parity. Now, if I take angular momentum, which is r, or x, let's call it x, vector x cross vector p, and I apply parity to it, what will happen?
The sign won't alter.
Yeah, the sign won't alter, right? So this is not a vector. These things are called pseudo vectors.
Pseudo.
Yeah, okay. Pseudo vectors or axial vectors, okay? Okay. So anyway, that was a side note. Let's move on, okay? So those are our examples of observables from the discrete case and the continuous case.